as just a word, what does projection mean? And when I say projection, she's like, wow, I went through that with my boyfriend or partner. It's bad. No one got it.
I thought about saying it, but I wasn't gonna say it, but you did.
Let's see. What does that projection mean? Simple, regular case, person's taking all the emotions, whatever, projecting onto another person. Another case in real life. Give you a hint.
Projector thing.
Projector, right? When you're at home, some people have projection rooms, right? So you have video, you're projecting onto the wall. All you're doing is pretty much taking a bunch of color vectors and projecting onto that space, correct? So in math, projection simply means you are taking a vector, projecting onto another vector. Good? Okay. As always, we're going to start with the 2D case. Easier to understand. And then we can extend. So we've got vector B and vector A, and I can project vector B onto vector A. Good. So if I took this, projected it down, where will it land?
On the x-axis.
Very good observation, Chris. I thought I was saying the z-axis. Certainly the x-axis, but where? X-axis could mean anywhere. Could it be here?
You're gonna go directly down beneath it.
Directly down?
You're gonna pretty much count only the x coordinates of the vector.
Huh?
You're gonna count like only the x parts of the vector.
Yeah, so I'm going to do the simple case and then extend it to the third dimension. It's happening to me. Good. So. Good. Easier way to remember, well, cinema, you're projecting on. Another case would be, shadow. If you have sunlight, your body is being projected to the ground as a shadow. Yes, those are all projections. So this vector is a projection of B onto A. I want to find what this is. How do you find it?
Do you start with what vector B is? Like, do you know what that is to find it or no?
Okay, how about this? I'll give you an angle, Peter.
You just put Pythagorean theorem or some trig identities. Or
Okay,
all sort of thing.
say going back to Pythagorean theorem, what is the length of that?
Is it magnitude of the vector?
Okay. What is the length of that?
The J vector?
Why the J vector, Rachel?
Because it corresponds to the Y.
It corresponds to the y-axis. Why can it not be something other than J? So that's the hypotenuse. Yes. So
Oh, I was
hypotenuse
thinking of
is B, And if I have to get B, it should be this squared plus that squared, and then you take the square root. In terms of components, what is the y component here? Arbitrarily speaking, I'll call it B2. Arbitrarily, this is B1. And that point right there would be B1. Yes? But if someone wanted to write this in terms of theta, how would you write it? How would you write B1 in terms of theta? B2 in terms of theta?
Cosine theta.
Come on, Kanza. It's Tamil Newman. You're in the right direction. Cosine theta something. Want the component B1 expressed in terms of theta.
Is it B1 is equal to the magnitude of B cosine of theta?
Do we agree? From last time? Okay, B1 is simply the magnitude of B times cosine theta. What is B2?
Same thing but sine.
Okay,
Or
same
cosine 90
thing,
minus theta.
but sine the magnitude of B sine theta. But I don't like this, well, I actually like the sin business, but here, I don't want sin, so what do?
Complementary.
Do the complementary with respect to the y-axis. I'll just call it just good, the complementary angle. But all that matters to me now is this. B1 right over here. So this point, this vector is the B1 vector, which is the magnitude of the vector B1 times the I vector. Yes, 1, 0. I can simply write it, the magnitude of B times cosine theta. Yes? Now, I have another vector A. I haven't brought A into the picture at all. Yes? How do I bring A into the picture now that you see magnitude of B times cosine theta? Do you follow my example? So what is the dot product between vector A and vector B?
A sub 1, B sub 1 plus A sub 2, B sub 2.
Okay, if I simply want to write A dot B, what will that equal?
Magnitude A times magnitude B cosine theta.
Magnitude of A times the magnitude of B times cosine theta. Yes? Now, B1 ends up being this part. Do you agree? So I can rewrite this. A dot B divided by magnitude of A. Good so far? Okay. Theta is an angle. So cosine theta is going to be a number. Agree. Magnitude is it a vector or a number?
It's another.
It's scalar. It's a good word, Haley. Scalar. I'm going there, so to help you. So that's a number in the sense scalar. That's also a scalar. You multiply both together, you get scalar. Yes. So we call that part called the scalar projection of vector B on to vector A. Looking for a vector. We have the scalar projection of vector B onto A. It simply gives a component of the vector B1 with me. So we call this the scalar projection as the component of B onto A. Yeah, we both use this representation. Comp B onto A. Give you a second to copy. Haven't gotten far yet. We'll get there. I want a vector. This one. So could I say B1, the projection that I have, I'll call it C1I vector plus C2J vector is this vector right here. Agreed. So that is B1I. So first component would be some number, second component is just 0. Yes. But this is going to go away because that is 0. I have C1. Is it possible for me to write C1, which will simply be B1 in this case? Yes, because whether I write it as B1 or B1I vector, one and the same. With me? Because there's only one component. So this goes away, C1, B1, one and the same. Same as B1. My question to you is, could I write B1 in terms of A?
Well, you can scale A, so it's the same direction of magnitude as B1.
Louder, Chris.
You
Well,
can-
correct.
You can multiply A, vector A by a scalar, so it has the same direction and magnitude as B1.
Okay, going back to the beginning of class today. I vector, the first one that we did, 8, 0, 0 was simply a stretched version of I vector in 3 dimensions. Yes. So A here is simply a scalar product of I.
Are you trying to make B1 a unit vector of A?
That's exactly where I'm going. Sorry. So by all means, if I find the unit vector of A, then pretty much I'm going to come up with A divided by the magnitude of A, yes? I can also write it as times I vector, because that's a unit vector also, correct? So A divided by the magnitude of A is simply the unit vector of A. B1 can be expressed in terms of A over magnitude of A. Why? Any thoughts as to why?
Because it equals one,
Huh?
because it equals one, so you just get the I.
What do you, okay, so what I'm saying is I can take B1
Hmm.
and express it in terms of this. How and why? Okay.
Because they're both composed of only the I vector.
Both of them are composed only of the I vector. This vector pretty much is a stretched version of that. Naturally, A happens because of the scalar multiple of B, agreed. Multiply by some value here, bigger than 1, you go there. A, some number less than 1, you come here. So I already have that expression A dot B over magnitude of A. What did this correspond to? B1. Yes, by all means, that could also be the magnitude of B1. Yes, no, maybe. Okay. This is the same as the magnitude of B1. If you take the magnitude based on what we wrote, it's still be B1. I'm going to stretch this and say, well, unit vector of A. I'm concluding that whatever I have up there as B1 is this number, which is a number that scales the unit vector of A. Good. Now, to connect the dots, I'm going to go back to that first problem that we did earlier today. 8, 0, 0. Do we all agree that 8, 0, 0 is a scalar or scaled version of I vector?
Yeah.
Yes? Okay. Is it also a scaled version of 2, 0, 0? Yes?
Yes.
All I'm saying here is 2, 0, 0 is A. Good. Same case. Interval 2, 0, 0, so you can connect this to this. We're going to go down 16, 0, 0. 16, 0, 0. Is that a scaled version of 2, 0, 2, 0, 0? Yes. So the reverse would also apply that 2, 0, 0 is a scaled version of 16, 0, 0. With me? So this part is simply scaled by that vector. Yes, by some value. Same argument. This vector is a scaled version of that vector. Now, all we want to know is by what amount. And that amount is simply the magnitude of B1. Good. A dot B of times cosine theta, or magnitude of B times cosine theta. The outlet come into play, which the formula is A dot B divided by the magnitude of A. A over at magnitude of A gives us the unit vector of A. Agreed. If I asked you, what is the unit vector of 2, 0, 0, what would you tell me?
2 I vector. I'm sorry, I vector.
I vector, right? Our first problem. What is the unit vector corresponding to 8, 0, 0? I vector. What is the unit vector corresponding to 16, 0, 0? I vector. What is the unit vector corresponding to 2, 0, 0? I vector. Yes. But I can write 8, 0, 0 in terms of a unit vector of this vector 2, 0, 0, which is simply I. But if I pick a vector that lies on this plane, hypothetically speaking, do you believe that the unit vector of this will still be I vector? No. And it would actually contain I and J. Agree? If I can do this, where this vector is in the same direction of the unit vector here, I can do the same thing for any vector on any plane. Do you agree? So hypothetically, if that is one vector related to ours, call it A. Sorry. I'll call that A, right? I can say that B is in the direction of A, yes? And it is some multiple of the unit vector corresponding to A. Yes, I'll do a numerical example too. So all I'm doing is I'm taking the unit vector for A and multiplying it by magnitude. So pretty much I'm getting a vector that is in the same direction as the unit vector of A. There, I simply had a number, so we call it the scalar projection of B onto A. Here, I took that number multiplied by the unit vector. This is the vector projection of B onto A. Good. That is called the component. This is called the projection. Projection of B onto A. Specifically speaking, vector projection of B onto A. Let me pick numbers. Call this 2. Four, yes. 8, 0. I can pick a different number. I want to keep things simple. Good. So A1, A2, 0, B1, B2. So I can write this. What is theta? Or how do you find theta?
Divide by the magnitude and do the inverse.
Well, I've given you the vector here, 2, 4, and this one, 8, 0, 2, 0. I want to know theta here.
Inverse tangent,
We can do inverse tangent. What is the length of this?
4,
4. What about that?
2,
2. How do we find the angle?
inverse tangent of 4.
Inverse
2.
tangent, or inverse cosine, or cosine, trigonometry, right? Let's just say you have an angle, and I'm going to do this. Find that value, the vector b times cosine theta, where vector b, excuse me, magnitude of vector b. Vector b is 2, 4, 2i vector plus 4j vector. Vector a is 8, 0, 8i vector plus 0j vector. I have the scalar projection of b onto a as this. I got it from here. What is the dot product of these two? That's easy. You can write it out, but dot product of vector A and vector B. Oh, louder. 16 what, Joe? Joel, Joel.
I vector.
Huh?
16 I.
16 I. So all I have to do is say Joe and then ow. 16 I vector. Do we agree? 2 times 8, 4 times 0. 16 I vector. If I took the magnitude, the I is going to go away. And the product is 2 times 8 plus 4 times 0, which is 16. 16 goes here. But before we get to that, what is the unit vector corresponding to the vector A? That's easy.
1, 0.
Huh?
1, 0.
1, 0. Why is that, Matthew?
Because it's on the X.
X-axis. Going back to the beginning of class, this, that. I vector. Projection of B onto A is simply that value A dot B divided by the magnitude of A. What is A dot B? 16. What is the magnitude of A?
8.
A. That is a vector. A is a vector. And we normalized it by its magnitude. We ended up getting I vector. So I vector. Yes? And what is 16 over 8? 2. Following so far? 2i vector is nothing but this vector right here. Yes? One and the same. This is 2, 0. Get 2i vector. So the projection of B onto A is simply the unit vector which points in the direction of A, scaled by this value right here. So I pretty much expressed this length using that and the unit vector of A. This is an easy case. I picked this so that it's relatively easy because the unit vector of A is simply the I vector because x-axis. No matter what vector you pick, I vector. Agreed? So it has to be some multiple of the I vector. In this case, that multiple or scalar is 2. Good. Component of B onto A will simply be 2. Unit vector in the direction of A is I. With me so far? Great. Well, might seem pretty silly, and you may ask me, what's the point of all this? I picked an easy case so that I can do this, and it's easier to understand. What if, going back to second day, third day of classes, have a vector in the standard plane, I can rotate it any way I want, and the same properties will hold true. Do we agree? Yes? Okay, that's exactly what I'm going to do. Some vector A, some vector B, projection of B onto A. I'll call it C. Yes? C is the projection of B onto A. The component would simply be the magnitude, agreed. Scalar projection will give me the length. Vector projection will give me the vector. Now, in the previous case, the one I picked, the unit vector in the direction of A ended up being I. Life was easy. Yes? Do you believe that the unit vector in the direction of A here will simply be I vector? No. Will it simply be J vector? No. It is going to be a combination of I and J. Yes? So if I want to find this vector projection, its magnitude, scalar projection, or component of B onto A. With me so far? I'll go with the simple physics engineering example, and then I'll start with the statistics example next time. Think of it this way. You might have done this in pre-calculus. You are the side of a runway at an airport. The plane pulled in, and then at some point it takes off and goes this way. So it is climbing, but diagonally. And you start to wonder, well, if it's going this way, vertically at an angle, what distance could it have traveled this way? Yes, if you wonder. Well, that distance at any given position is simply the projection. Good, that's a simple case, simple example. I'll explain another one with statistics next time. Do we follow? I picked the easier case first because easy to understand. So the key here is the projection is simply a vector that is in the direction of the unit vector of where it's getting projected. Good. Okay. Stop that and pick up